What we are going to study today is thermonuclear fusion. So the word thermo basically comes from thermal. So nuclear fusion, which happens because of the temperature factor, is basically referred to as thermonuclear fusion. And you know that if you want to have two nuclei fuse together, you have to apply some energy, right? So what kind of energy you apply, depending on that, the fusion will happen. So when we talk about the sun or the stars, that the reaction that is happening is nuclear fusion. And from our preliminary knowledge, we do know that there is generation of enormous amount of energy after a fusion happens. Now this fusion actually happens in a cycle. Okay? So the probability of having helium is more, but then there are also chances that you might have other nuclei like beryllium, lithium, and so on. But just look into it from a mathematical point of view. If you remember the last class we discussed that whenever a heavy nuclei breaks into two, the nuclear force is being overcome by Coulomb force. You have two nuclei, their nuclei are separated out, their nuclei are positive, okay? So they will actually repulse, which will be Coulombic in nature. And if you can overcome that Coulomb repulsion, then while combining, nuclear fusion will happen. Okay. So the thing is, we have to overcome that Coulomb repulsion. So the first task is to measure what is the Coulomb potential that exists. And if the energy that is given as an input is more than this Coulomb repulsion, we can actually have nuclear fusion. This was the idea. Okay. So we're just going to continue a bit with that. Okay. So what happens is here we are using a thermal energy, thermal kinetic energy for fusion. Okay. So thermal kinetic energy for fusion is basically used. And this thermal energy will actually provide enough energy for the fusion to happen. But you know, when we do our calculations, we see that the Coulomb potential that is there is far greater than the energy that exists within the sun. So if that happens, that means how can there be fusion reaction? Okay, so this is what is the aim of today's lecture, and let's try to have a look into it from a mathematical point of view. So the first thing is we use thermal kinetic energy for fusion, and this is usually the reaction that is going on in the stars. Okay, so this is usually the reaction that is going on in the stars. So this energy is usually provided by the temperature in the stars, hence thermal. So you know the temperature is quite high. And let's just look into a calculation. So let's say at room temperature, okay? So this is just an assumption. We have the room temperature, and you know all the measurements are in absolute units, so it is 300 Kelvin. We can actually find out this value of kT, okay, which is actually nothing but 0.027 electron volt if you do your calculation. So you can put the value of Boltzmann constant, put the value of temperature as 300 Kelvin, do the calculation, you get that 0.027 eV. Okay. So you know whenever we are doing this calculation, wherever there is a unit of kT, we usually measure it as a unit. Okay. So at that particular temperature. So basically we have it as the scale of energy. That is usually taken convention. Okay. But then if you remember from your statistical mechanics, the kinetic energy per molecule per degree of freedom is half kT. Okay, if you remember this is done in your statistical mechanics. Okay, and this is something which we derive from law of equipartition of energy. Now here also we are talking about molecules, right? So obviously this is valid. So if you are considering a one gas molecule and you want to find out what is the kinetic energy per molecule, it will be 3 by 2 kT. Why 3? Because 3 degrees of freedom. So we have got 3 by 2 kT. So let's just keep this in mind. So what happens is at room temperature, this kinetic energy is too low. So if you just consider the room temperature, this is the kinetic energy available. This is a very low kinetic energy. Okay, this cannot overcome the potential barrier, and we cannot expect that there will be a fusion reaction. Okay, so what happens is this is the average kinetic energy, which we already know. Okay, this is the average kinetic energy which we have already seen. But then 0.027 eV is very low compared to the barrier height. Once again, what is this barrier height? This barrier height is nothing but the Coulomb potential. It has to overcome that potential. Then only fusion will happen, right? So the question is, what should be the temperature? Okay, what should be the temperature so that it can overcome the barrier height. Okay, it can overcome the barrier height. So if you have a temperature and you know what is the temperature needed to overcome the Coulomb potential or the barrier height, then only the fusion reaction should happen, at least theoretically. Okay, so let's just look into it, that what should be this temperature. How do I find out this temperature? Very simple. I should know what is the barrier height, and then I can use the formula law of equipartition of energy and then find out what is the temperature. Let's just do that calculation, already done. Okay, if you look into the screen. So average energy of the proton, let's say we have 1h, so that's proton, right? 1h in the sun, in the stars. Okay, so we have got one proton whose average energy is 3 by 2 kT. And you know, proton, the Coulomb barrier that happens is approximately 150 keV. We did some calculation in the last class. You can anyway do it, right? Z1 Z2 E square divided by 4 pi epsilon naught R, where R can be calculated from R naught A to the power 1 by 3, right? So you can do all your calculations. You'll see the range is 150 kilo electron volt, 10 to the power 3. So now I know what is K and I know what is the Coulomb potential, and then I can do my calculation and find out what should be the value of temperature. So what happens is that in a single line, if I say the temperature is such that the average kinetic energy, which is 150 keV, should be overcome. Okay, and that is actually will be nothing but the comparable to the barrier height. Idea is simple: put some energy, it should overcome that barrier height. So if you measure this temperature and do your calculation, this becomes 100 keV, because 150 into 2 divided by 3, 100 keV, divided by, you can put up Boltzmann constant, 8.6 into 10 to the power minus 5 into EV per Kelvin. Okay. So if you do this, approximately the value is 10 to the power 9 Kelvin. It's a very, very high temperature, right? But then if you have read this, the temperature of sun is not that much. It is not 10 to the power 9 Kelvin. Okay. Obviously, this is an idea which we actually got. See, the idea of equipartition of energy, statistical mechanics is done on the Earth. But then, once you have developed this idea of the temperature, okay, what should be the temperature, and also we know how to find out the Coulomb barrier, we can easily estimate what is the temperature of the sun, or what should be the temperature in the sun. Okay, and that is the beauty of physics. Okay, that is how we do some estimations even without going to that physical place. But then when the spectroscopic techniques are used, you know that the sun will emit certain radiations, right? And basically when you are using spectroscopic techniques, you will get those hydrogen lines. And based on this, you can say, okay, depending on the wavelength, you can say what will be the temperature of the sun, right? So those calculations were done, measurements were done, and it was observed that this temperature of the sun was not 10 to the power 9 Kelvin, it was 5 into 10 to the power 7 Kelvin. So 10 to the power 7 Kelvin was the temperature. So there is a 2-order difference, huge difference. So I cannot have kinetic energy or enough to actually overcome the barrier, okay, or the thermal energy enough to overcome that barrier. So if I consider the temperature to be 10 to the power 7 Kelvin, if I take this value, the energy that is available is 1 keV, but then it has to overcome a barrier of 150 keV. Okay, so this is obviously much less than 150 keV, 2 orders less, because this is 10 to the power 7, that was 10 to the power 9. So what is the reason being the, so this is still small compared to 720 keV, because of some other model also 720 keV is also an energy range, but then the order is same, so don't worry. But still the sun produced fusion reaction. Okay, now why does this happen? Now, you know, if you consider something like boiling point of water, if you want to boil water, so usually what happens is the temperature that you have is 100 degrees centigrade. But if you use a pressure cooker at home, okay, if you are cooking and if you're using pressure cooker, what happens is the steam that is generated within the pressure cooker will actually create a lot of pressure inside that. Okay, that is why it's called a pressure cooker, and because of which this boiling point comes down. So if the density is very high and they are very closely packed, that means the pressure is very high. If the pressure is high, the temperature required to overcome that energy comes down, right? So this is what happens in the sun, because it's not 1 or 2 protons, there are millions of protons there. and it is compressed within a very small region, and that's why even if the temperature of the core is 10 to the power 7, remember temperature of the core, okay, core is an important word. Even if the temperature of the core is 10 to the power 7, still fusion reaction happens because of the pressure, okay, because of the pressure. So that is what is happening. So that is why we usually consider that that is the idea that we have, and we have seen it that this is possible, and that's why the fusion reaction happens in the sun. So the simple reason is the density is very high. So I think you can easily guess the question now, that why does fusion happens in the sun even if the temperature is not as per the desired limit to overcome Coulomb repulsion? The answer is, at the core the pressure is really high because the density is high. Okay, so density is high, hence more pressure. Okay, so that's important. So this was actually the mathematical idea and the theoretical idea based on which we can say that yes, fusion happens in the sun. So you see, when we try to realize the fact that how do scientists really work, so that based on some theory they are going to predict something which is so accurate and so close to the reality. Okay, so this might be a good example to understand this. A lot of predictions which we already know, but based on this we can easily say that why does the sun has a good chance of resulting in nuclear fusion reaction. Okay? So if you basically plot a graph, okay, and then you plot a graph between the number of let's say molecules, okay, and of course the velocity, and if you plot the velocity on one side, that means you are plotting the kinetic energy value. Okay, so if you follow your statistical mechanics, you did use the relation k is equal to half mv square, and then you used some relation which is called average energy. This term you have used in quantum mechanics also, and then when you do your calculation keeping all the statistical constructions in nature, you find out that this is nothing but half kT. So please go back and revisit your statistical mechanics. If I'm not wrong, you did too, partition of energy. Okay, so there you get this result, so don't get confused, this is already done. So 3 by 2 kT is the maximum number of molecules, the energy of maximum number of molecules. But the energy might be distributed somehow. Okay, so there will be some molecule which will have here, okay, the energy is far greater than the average energy. This is the average energy, please remember. So maximum molecule will have an average energy. Okay, so if I take a class of 100 students and I measure the marks, I take the average mark, maximum student will be near that average. That is the logic, right? Statistical logic. But then whenever you do statistics, you have to have a lot of data. So there are a number of molecules there. Okay, but then there are certain molecules which will have higher energy. Okay, so that is also possible. So the sun is basically a very dense system. So this happens more in case of sun, since the density is very high. Okay, so if we have more higher energy molecules, there are also chances that the probability of barrier penetration will be more. Okay, higher probability of barrier penetration. Okay, energy is this, but then there are also higher energy molecules which will also result in a fusion reaction that happens. Okay, so this is a very basic theoretical idea. Okay? And based on this, we can actually talk about the cycles, okay, that happens in the sun. So this is the basic of nuclear fusion that happens, and this is what is the mathematical idea is all about. Okay, so let's just have a look at fusion reaction that is happening in the sun. Okay, so neutrino is something which was not initially detected. Okay, it was very difficult to detect neutrino because it does not interact with the human body. Okay, and the interaction of matter with neutrino is minimum, and that's why it's more difficult to detect. So this neutrino was also seen in the fusion reaction. Now, what were the things which led to the detection of neutrino, or why we said that okay, neutrino should be detected? Okay, we talked about beta decay and all. That is something which we'll study later in the next unit. Okay, so let's just look into the fusion of fusion reaction that is happening in the stars. And by stars, I definitely mean the sun also. Okay, so it is happening everywhere there. So fusion is probably the basis of all life forms. Okay, fusion happens in sun, because of which we have the sunlight, which makes life existent. So probably from our moral ground, being a student of physics, learning fusion is important. Okay, So the mass of the sun is 1.99 into 10 to the power 30 kg. Okay. Of course, you don't go to the sun and measure it. Okay. There are indirect ways of doing it. Okay. You can always use the relation F is equal to G m1 m2 by r square. Okay. Those sort of relations to actually measure the mass. So this mass was actually 10 to the power 20. If we consider the Earth, it is 10 to the power 24 kg, 10 to the power 30 kg. So that means that is 10 to the power 6 times greater than the Earth. Okay. But then if you look into the diameter, this is 10 to the power 6 kilometer, which is 109 times diameter of the Earth. These are just some parameters. We are not going to do any calculations. Okay. Just let's be a bit aware of the sun and the Earth's dimensions. So what is the mean distance of the Earth from the Sun is 1.5 into 10 to the power 8 kilometers. Okay, so we're just talking about what is the parameters that is related with the Sun. Okay, and if you look into the composition of Sun, I think this is something which you already know. Okay, if we look into the composition of the Sun, okay, so please pardon my handwriting. Just listen to what I say. You have the hydrogens. Okay, that is almost 73.46%. And you have helium there, which is 24.85%. So most of the reaction, the final resultant is helium, okay, which you know is stable. If you remember binding energy curve, it will definitely give you a peak, and this stability actually results in the helium nuclei. Okay, so this helium nuclei is also there, 24.85, quite a substantial amount. But then these are not the only two elements that are present. Okay, there can be oxygen, there can be carbon, there is even iron. Okay, and in intermediate reaction, you do have beryllium, you do have lithium. Okay, but then the amount that is present is very, very less. If you want to divide the sun into zones, okay, there are usually 4 zones. So this is the first zone, okay, which is basically called the core. Okay, and the temperature of the core is 1.5 into 10 to the power 7 Kelvin. So I think you understand that the reaction that happens in the core, because of which this much of enormous amount of energy is being given out, okay, by the system. So we have got 1.5 10 to the power 7 Kelvin. That's the temperature of the core, and this core, the radius is very less. It is less than 0.25 the entire radius. Okay, the entire radius. So if we just consider, so that means if you consider the entire sun, 1/4 part, okay, will be actually having the core. Okay, and this is where the fusion happens. So I think all these point wise that I've written is important to just remember the things. Okay, and in exam you can easily frame some sentences and definitely write it down. Okay, I've compressed all the information in just a few lines. Okay? Next, the next zone is radiative zone. So it basically has the uh, energy radiation. Okay, the energy radiation that happens is basically the radiative zone, and this radiation happens up to a distance of 0.7 r. Please remember this. Okay, so this is your second zone. So from 0.25 from this region to this region is nothing but the 0.7 r value, which is the radiative zone. The third zone is convection zone. You know, heat can flow. Okay, convection, conduction, convection, radiation, if you remember, and convection is also there, convection zone. Okay, so what happens is the convection zone is lies between 0.7 r to 500 kilometer. Okay, so if you consider the entire radius, you have this much region, which is the third region. Okay, so this is the convection zone. Okay, don't just look into the scale of the diagram, it's really bad. Okay, it's just a representation. And if you go outside that region, outside this convection region, okay, uh, that means you go to the surface of the sun, you have got something which you call the photosphere. So, you know, if you look into the atmosphere, ionosphere, those levels, okay, and if you go more and more towards the sun, and if you cross the atmosphere and the ionosphere level of the earth, you actually reach a point where we call it the photosphere. So, you know, photo means photons, right? So you have existence of photons there. Usually it doesn't need a medium to travel, and that is the reason that heat can travel, okay, with photons. Okay, that is basically nothing but heat is a form of energy, so that is the carrier of energy. So this is the 500 kilometer zone, beyond the 500 kilometer zone. So that is beyond 500 kilometer from the surface. So here we have got the fourth zone, which is the photosphere. So this is a very basic brief of how is the sun constructed, okay? And I think we should know it, very important, since we're talking about fusion and sun. So it's very important that we know what exactly happens in the sun. Okay? Let's just look into some reaction that happens. So before I start, there are three cycles, okay? So three cycles that happens. A possible question for your exam might be, I might ask you any of the one cycle and you have to write down the reaction scheme, okay? And that is very important, okay? So where exactly the cycle or the reaction happens, as I said, that happens in the core, okay? And if we try to understand the core a bit better, okay? Uh, I think this is something wrong, okay? This is 10 to the power 7 Kelvin, not kilometer, something wrong over there. Anyway, the pressure is 200 billion atmosphere. The pressure is 200 billion atmosphere, huge pressure. And if you consider the states of matter, solid, liquid, gas, and then there is a fourth state of matter, which is called plasma. The plasma exists at a very, very high temperature, okay? Even if the pressure is more, the chances are there that there will be a plasma state. So what happens is in a plasma state, usually you don't have the atoms, okay? You don't have the nuclei formation. You don't have the electrons bound to the nuclei. The electrons are away, okay? The electrons are totally free, and then we do have the protons which are existent. So if you're basically considering a hydrogen atom, you have all the protons there, okay? And that is what is the core is all about. This is basically existing in a plasma state, okay? And if you do a comparison between the temperature of the core and the photosphere, you see this. Photosphere 10 to the power 7 Kelvin. Here it is 5780 Kelvin. So it is just 10 to the power 4, right? 10 to the power 3, sorry, 5780. Order is 10 to the power 3. Here the order is 10 to the power 7. So drops drastically. Look at the pressure, 0.1 to 0.001 atmosphere. So that means the pressure and temperature drops so drastically that you cannot expect any kind of reaction happening there. So whatever energy we get generated, everything is generated in the core. And then by the physical process that we know, it is being transmitted from one layer to another. And based on this, it will actually finally reach the Earth's surface for our survival. Okay? So that is what is happening. So having said that, let's just go for the first reaction cycle. And the most probable reaction that actually happens is actually should result in the formation of helium. Okay, so one of the most prominent reaction that happens in the sun is this. You do have a lot of hydrogen atom because we are talking about the plasma state at the core. Okay, so we do have the protons which are coming together and fusing. Okay, so hydrogen, okay, and see all these are probabilistic. It's not that all the reaction schemes that we will discuss now will be equally probable, but then there are chances. Okay, it happens, it releases a huge amount of energy. Again another reaction happens that will release another huge amount of energy, and all of these reactions will keep on generating energy, and the cycle will keep on continuing. Okay, so there is a cycle that happens. So you've got hydrogen, it will give you basically deuteron, okay, and then it will give you beta emission, okay. So you do have an electron, a positron coming out of it, sorry, not electron, and a neutrino, okay. So this is important, okay. You know neutrino, the idea is still not clear because we have not discussed it. We'll discuss in the standard model. So then we have got the time scale. Now this happens 10 to the power minus 20 seconds for the reaction. So it doesn't take that much of time, okay. It is actually a large scale if you consider from a nuclear point of view, okay, nuclear physics point of view. But then this reaction time is there because we have got it under enormous temperature and pressure. And definitely it's under enormous temperature, so the chances of fusion are there. And then we have got the proton-proton reaction happening. So we have the proton-proton free, but then there are so many protons there that the chances of collision are more and fusing are also more. As soon as it fuses, releases energy. We have got 2H1, and then again 2H1 combines with another 2H1. We get 4He2 and so on, and the reaction keeps on happening. Okay, but then there is one issue that we need to address, and that is called the deuteron bottleneck. You know, any kind of experiments, okay, if there is a bottleneck, that means there is some kind of restriction that happens. We need to understand that system, okay, and then we need to predict that whether this happens or not. Okay, what is that bottleneck? It's not that all the protons will fuse, because you know most of them has got the average kinetic energy. They don't have the high kinetic energy. So the higher kinetic energy protons will fuse. First point. Second point, when basically this fusion happens, okay, because it's in the plasma state, so the chances of having the fusion is again very difficult. So if we just take a value approximate, it's seen that 1 out of 10 to the power 18 proton fuses. So 10 to the power 18 protons are there, and out of that only one proton will fuse, okay, and with another proton. So you can look into the probability of a proton-proton fusion happening. But then why we get this much of energy? Because the number of protons are very high in number. Okay. So if even if the probability is low, the number of protons are very high. So if you consider a class of 100 students, you take the average, okay, you see that the average might vary statistically. But if you take a class of 1000 students, you will see that the average will be more and more closer to the number of students who actually have got that many marks, okay, or near that mark. So, you know, statistically, number of values are more, it's very important. So that means even you can see this example now. Nuclear physics and statistical mechanics are also very important. So we do have 6 to the power 6 into 10 to the power 11 kg of hydrogen, okay, and then if you consider this much of amount and use the Avogadro's number, find out how many protons are there, you can see, okay, we can actually estimate that there are 3.7 into 10 to the power 8 protons that fuse every second. So now we have got a number of protons fusing every second to generate enough energy. Okay, so this is the theoretical idea. Just let's look into this reaction now. Okay, we're just going to look into one cycle now, and then next class, that's day after tomorrow, we're going to look into the other cycle. So just let's have a look at this scheme. So you have got one hydrogen combining with one hydrogen, you give 2H1. You have got another set of reaction happening somewhere, okay? So you will have 1H1 there also, okay, from there, or you can have a 2H1 from there also. We're going to look into that reaction. So this 2H1 when combines with 1H1, it will give you tritium, oh sorry, helium 3, okay, helium 3. So 3He2 plus gamma. So it'll give you some kind of radiation which will come out, okay? And then of course it also generates energy of 5.49 MeV. Okay, and then you have see, all these reactions are happening simultaneously. So it is not that there is only one reaction happening. There will be a number of reactions happening which will give you this. So the chances are that there is one helium 3 which will fuse with another helium 3 which is coming out from another reaction. And these three will combine, these two will combine, and then they can give you 4 helium 2 plus 2 hydrogen atoms separately. And this will again generate 12.86 MeV energy. The chances of this reaction happening is 85%. So now we understand that this reaction will be maximum. And you know, this is not the percentage that we usually can estimate easily, because there is, even if you consider 1% of a reaction happening, that means there is an enormous amount of energy generated, because there are large number of protons, large number of helium 3, helium 4, and so on. Okay, so even 1% is also quite large. Okay, so if I tell you I'll give you 10% of my 100 rupees amount that I have, it's only 10 rupees. What is the use? But then if I have 1 crore and I tell you I'll give you 10%, then you will say, oh, that's a substantial amount, right? So that, you know, even the base amount, the principal is more, definitely the interest will be definitely more. Okay, so the rate is very important. So then we have this 4 helium, and then we have, let's say, 1 helium 3 from this. There are chances that this 3 helium will also react with 4 helium. These are all energetically favorable reactions. Okay, and if this happens, the chances are we will get beryllium. See, 7Be plus
Sir,
gamma. Okay? And the chances of this
sir,
reaction yeah, is 15%. Yeah.
sir, the principle of hydrogen bomb and this principle are same, sir.
Yeah, partially, yes, because you know, when we talk about hydrogen atom, that is also hydrogen bomb, that is also dependent on fusion reaction, and fusion reaction usually generates a enormous amount of energy compared to fission reaction. Okay, so there are even if you look into the destructive part, there are different kinds of bombs that are created depending on fission and fusion. Okay, so yes, answer is true. So that much amount of energy will be generated. Okay, so you can understand that that much amount of energy is generated in the sun, which is able to sustain so much of livelihood on the earth. Okay, apart from, of course, other factors that actually happens. Okay, the universe, existence of the universe. Okay, a lot of things are happening, stars and everything are there. So if that kind of reaction happens on the Earth, it's just going to be within a few milliseconds that everything is going to get destroyed. Okay, so that means obviously the scale is not that high, but if you consider examples of these hydrogen bombs and all, the scale is enormous. Okay, so obviously that is exactly what is happening. Okay, so that's there. Uh, then this is the cycle. This is the first cycle, which is the proton-proton cycle. Okay, so this is important, and this is one of the questions that I have asked in the last semester, the proton-proton one cycle. Okay, and explain the reactions that is happening. So if we are actually going to get 3 helium and 3 helium combined to give you full helium, which is the chances of having 85% reaction, that means you should get 3 helium 2 from somewhere and 3 helium 2 from somewhere. So two separate reactions will happen. This will happen. You will get 2H1, and then this reaction will again happen to give you 3He2. Then another reaction happens somewhere, and then you can get another 3He2, right? So two such reactions should happen. Okay, I think this is clear. You get 1H1, 1H1, 2H1. Forget about the rest part. It definitely have to write it down, but we are just concentrating on the hydrogen and the helium part. And then we can take 2H1 from here, and then there is one proton which is loitering around. It will again combine with this, will give you 3 helium 2. So you need these two reactions to happen so that you are getting 3 helium 2 or helium 3. And then you should have two such reactions which will give you helium 3. So you should have two such reactions. See, one, this should happen twice. This also should happen twice. This also should happen twice. I'm just considering one cycle. That is why that is called a chain. And when this reaction happens, finally you get the helium, which will actually generate that much of energy. And of course, 1H1 plus 1H1, whatever scheme I've shown it before. So we basically, if we just break it up, we have got the final output as 4 helium. Okay, and initially there are 4 hydrogen atoms or 4 protons that are getting involved in the reaction. Okay, and then you can do the balancing and all, and this is the first cycle that usually happens. So this is the first proton-proton cycle. There are 2 more cycles that happens. Okay, and then I also mentioned that there is existence of carbon, oxygen, and so on. Does that happen in the sun? The answer is there, but it's minimum. Okay, but still we'll look into that cycle also. Okay.